last time, one of the things we did were we proved two mean value inequalities. So we proved two mean value inequalities. And let me recall those. And the first one was that, so if you had a function f on some interval from a to b into R, and this function f is differentiable, then it said that there exists some x0 with x0 strictly between a and b, so that the derivative at x0 is equal to the average of the function, or the average of the function at the endpoint. So this is the average on the endpoint divided, so it's average over the length of the interval. So this is what the mean value theorem said. And then there was a second mean value theorem, and that was the Cauchy mean value theorem. So the Cauchy mean value theorem. And that was where you had two functions, f and g, on this interval into R, and they are both assumed to be differentiable. And then again, it was that there exists some x0 strictly between a and b. And if you take the derivative at x0 of f times the value, the difference in value of g at the endpoints, then this is equal to the derivative of g at x0 times the difference in value of f at the endpoints. Right, so that was the Cauchy mean value theorem. So it's a little bit more complicated than the actual mean value theorem, because you had two functions at the same time, and the point here was that you can arrange this x0 to work for both points, for both functions. Right? Let me just make an observation that if if we're looking at So the Cauchy mean value theorem seems like a more elaborate version of the mean value theorem, and it really is, because if you suppose that g here was the function that is equal to x, so g of x is equal to x, I have f here on the interval from a to b. This is again differentiable. Well, if the other function was just this sort of rather trivial function g, of course g is also differentiable, and we even know that the derivative of g at all points is 1, right? So if you are now applying the Cauchy mean value theorem, then it say that by the Cauchy mean value theorem, right, there exists some x0 with x0 strictly between a and b. And so that the derivative of f, so that's whatever that is, that's the derivative of f at x0. The value of g at these two endpoints, well, g is just a function x, so this is just b minus a. And the derivative of g is 1. And then it's the difference in value of f at the endpoint. right? And so now if you just divide by b minus a, so this of course implies that f prime of x0 is equal to f of b minus f of a divided by b minus a. So in other words, and so you see this here gives you the more standard mean value inequalities. So in other words, the Cauchy mean value theorem is more general than this mean value inequality, right? Because you recover this if you just let one of the two functions be just a trivial function x. Right? Okay, so that was just an observation. The second thing I want to talk about is something we didn't get to last time, and this is these L'Hopital's rule. And I'm just going to state one version of it. There are two versions, and they're both in the notes, but I will just state one of them. And so this is, so the situation here is that you have two functions, f and g, and they are defined on some interval, say from a to b into r. The interval does not include the endpoint, okay? So these are differentiable. And then we assume that the limit here, we assume that g, of x is, and not only g of x, but also g prime of x are not equal to 0 for all x. And then we assume that the limit here of g of x as x goes to a, that this here is 0, and the same holds for the function f. So let's see. And then what you're interested in is that you're interested in looking at f of x divided by g of x, right? So this here makes sense. G doesn't vanish, so this here makes sense. And you are interested in looking at this fraction here as x goes to a, right? If x goes to a, then the denominator goes to 0, and the numerator also goes to 0, right? And the question is, does it have a limit or not, right? And so there's one more assumption here that you need, and that is that that if you're looking at the, so assume also that the limit here as x goes to a of f prime of x divided by g prime. Assume that this here exists and is equal to some L. Okay. And then the claim is that then, so the claim here is that this fraction here, f of x divided by g of x, that this does have a limit as x goes to a, and that limit is actually L. So this is one version of this rule, okay? And there's another one very similar. Okay. And so we want to prove this. So we are looking at, so we want to apply the Cauchy mean value theorem to prove this theorem. And so we're looking at an interval here. So you're looking at say, y. So here you have a, here you have x, and then here you have y, and here you have b. Right? And I'm now going to apply, so we will apply the, Cauchy mean value in. But we are applying it on this interval here. Between, so y here is less than x, but it's strictly bigger than a. And this is, x is strictly less than x, right? So the function was differentiable on this open interval, so of course it's differentiable, or both functions are differentiable on this closed interval. So we can apply it, and so we get that f prime at some intermediate point, x0, times g of x minus g of y. This is equal to g prime. Again, x0 here is some intermediate point that lies between these two. G prime at x0 times f of x minus g of y, sorry. Like that. Right? This is just applying the Cauchy mean value theorem. Sorry? What did you say? Oh, yeah, sorry about that. Thanks. Yeah, thank you. Right, and so now I just divide. Of course, this here is supposed to be non-zero, so I can just divide. So we have that that f prime of x0 divided by g prime of x0, and then I want to divide by this, but I just need to make sure that this here is that I can divide by it, right? That is not zero, this thing here. So I have this. Now, think about x as being fixed and do this for all y, right? If I do this for y, where y is very, very close to a, this here becomes really, really close to zero, right? This here is fixed and it's not equal to zero, right? So this here is very close to zero, this is not equal to zero. So this here, if y is really close, if x is fixed, y is really close to a, this is definitely not zero, right? So I can divide by it, right? So for x fixed and y sufficiently close to zero, then you have then g of x minus g of y is not equal to zero, right? And so I get that f prime at this intermediate point divided by g prime at the same intermediate point is equal to f of x minus f of y divided by g of x minus g of y. And now you see that as y here goes to zero, right? So x is fixed still. As y goes to, sorry, not to zero, but to a, this here goes to zero by assumption. This here goes to zero. So the whole thing goes to f of x divided by g of x. right? Now the thing is that if you, so this is for all x fixed. Right, so now so now we want to use, so now since f prime at say z divided by g prime at z, since this fraction here as z goes to a, this is assumed to go to L, right? So this means that given epsilon greater than 0, there exists a delta greater than 0, so that if z here is less than a plus delta, right, then this fraction here, then f prime of z minus g prime of z is minus L is less than epsilon, right? So now coming back here, if you were starting with, so this here again was for all fixed x, right? You had this statement, right? And again, x0 was between y and x, right? So now if this x here, if x is delta close to the left endpoint of the interval, right? Then you would have that x0, right? But x0, remember that x0 is lying here, right? So since x0 would lie here, this means that also x0 here is right is in this interval here, right? And so this means that this number here you get is L with up to some, it's L up to some error of like epsilon, right? So this here is almost equal to L. And so this means that this limit here, right, is almost equal to L within an error of epsilon, right? Okay, so this proves this version of the L'Hopital rule. And there's a second version, and that's in the notes, but I'll skip it actually for now, just because, that was sort of from the last lecture, and it's very similar to this. Yeah? Sorry, why?
Why do we deduce that gx minus gy is not equal to 0?
Yeah, okay. So this is because g of x is supposed to be not equal to x for all x, right? And now I'm fixing x. Okay, so this here is non-zero. Then I'm letting y go to a, but then this here goes to 0 by assumption, right? So you see that if you're fixing x and you just take a y sufficiently close to a, then this denominator is definitely not 0, right? You really want to let y go to a, because then this here is eliminated, right? This is not part of the statement, the g of y, right? Okay. And so again, as long as we started with an x that was sufficiently close to, right, if x was in this interval, then x0 is even further to the left, so this is also in this interval. We don't know exactly what x0 is, but it is in that interval, and so this means that this here is strictly smaller than epsilon. Okay, so another thing we talked about last time was this with the tail expansion. and that all of these things really came out of this Rothe theorem, and that was also the case for the tail expansion. So you have a function f. So this is just to remind you about the tail expansion. So you have a function f, and let's say that it's defined on some interval here into R, and the function is, so f here is k times differentiable. So this means that f prime exists, f double prime up to the k derivative, right? So they all exist. And then the statement was, so then you looked at the k minus 1. This is the k minus 1 Taylor polynomial. And it was given by that k minus 1 of x is equal to, and now you're summing here from I equal to 0 to k minus 1, and you take the I derivative, this is the I derivative of f, and you do this in a, and you divide by a factorial, and then you're looking at x minus a to the power I. Right? So this was the k minus 1 Taylor polynomial. And then the Taylor expansion just told you that f here at some x was equal to p k minus 1, this Taylor polynomial, plus, and then this is what is usually referred to as a remainder term. And this looked very similar to one of these terms. It was the k derivative of f, but then it was evaluated at a point c divided by k factorial times x minus a to the power k. And c here was supposed to lie between a and x. Okay. So that was this is the Taylor expansion theorem, right? And so the thing is that, so why is this so useful? And it is extremely useful in many different settings, also in much more general settings than what I'm describing here. And that is because that if you take a function here, then, and it may be a very complicated function, but this Taylor expansion theorem tells you that it is close to, if you want to evaluate it at some x, you can evaluate the Taylor polynomial. That's after all just a polynomial, so that's easy to evaluate. And then you get within this remainder term of the right answer. Okay, so that's how it always is used. And so the question is now, the natural question is, how well does the Taylor polynomial approximate the value of the given function? Right, so how well does the Taylor polynomial approximate the function? Okay, and of course to understand that, you need to estimate the remainder term. Let me write the remainder term here. So the remainder term, right, so the remainder term is, so I write this here as, so it really depends on x also, right? But I would just write it like this thing here. So by this I mean the k derivative of f in c divided by k factorial, and then x minus a to the power k. So again, it depends on really also on it. Of course, it depends on a, but it also depends on x, right? And it's this thing here. The catch here is that you don't really know what c is, right? The only thing you know about c is that c is lying between a and x. So this is essentially all you need, all you know. About c. Okay. So now let's look at some examples. Let's look at 2 examples. So the first one is like a promising example, and the second one is much less promising. So the thing is that how well it approximates really depends on the function. Okay. But the first one is quite typical, though, example. So suppose that the function f of x is the exponential function. And then we have that the derivative is just the exponential function itself. So this means that if you take the derivative k times, then you just get the function itself. So this means that the k minus 1, this means that the k minus 1 Taylor polynomial, right? This is just the value of the function. I'll just write it out here. So this is the value, and now I do it for a equal to 0. And I'm assuming that b here, so I will think about this function here, f of x, this function, the exponential function. I'm going to think about it on the interval, say from -1 to 1. Into r. Maybe I'll just take it from 0 to 1 into r. Okay, so the Taylor polynomial. So I'm going to so the Taylor polynomial one also talk about that this the Taylor polynomial is expanded around a. Okay, so we talk about that the Taylor polynomial. So we talk about Taylor expansion around a. Okay, and this just refer to that when you plug in a here, well then of course you have exact equality, right? And that all of the derivatives are evaluated at a. Okay, so it's really like the Taylor polynomial. It's only a good approximation near a, right? So I want now to Taylor expand near the 0. And so the value here of the function is 1 at 0. The derivative is, right, so the derivative is also 1 because it's just this function itself. And so this is, so you get x, and then you get the next element in the tail expansion is x squared over 2 plus x squared over 3 factorial, and then x to the 4th over 4 factorial, etc., up to x to the power k minus 1 over k minus 1 factorial. Right? So this is the Taylor expansion, or take k minus 1 Taylor polynomial around 0. Okay. And so now, if you are interested in evaluating P, you want to say how well does this here approximate the original function, the exponential function. So you want to bound this thing here, right? So you want to have a bound for that. Well, the thing again is that f of x, you know that f of x is equal to this Taylor polynomial, and then plus this remainder term, right, in the C, right? Now C again has to lie, C will lie between a and x, and in this case a is 0. So it means that C here, so this means that here, C here is between 0 and x, right? And the remainder term here, this here was equal to that you took the k derivative of the function. So in this case, the k derivative of the function is the function itself. So this here is the value of the k derivative, and this is at C. This is the k derivative of the original function. And then you have to divide by k factorial, and then it's x to the power k, like that, right? And so you see that if x here is now between 0 and 1, this means that this thing here, this remainder term here, the absolute value is, so C here is less than 1. So this means that this thing here is less than E. So it's less or equal to E divided by k factorial. This here is bounded by, since x is bounded by 1, this is bounded by 1. So you're getting this inequality here, right? And so you see that if k is very large, this is a tiny number, right? So it's a really good approximation. I mean, you don't even need to make k very large because it's exponential, right? Not exponential, it's factorial, yeah, right? Okay, so that's a kind of encouraging example. Let's say that the Taylor expansion is a very, in this case, is a very good approximation to the function. Another example that is less encouraging, and so again, the moral is that how well the Taylor expansion approximate the function depend on the function. So suppose that the function here was the function that was 0 here when x is less than 0, less or equal to 0, and when x is bigger than 0, then it is e to the minus 1 over x squared. Okay? So you see that when x becomes very, very small, you are looking at 1 over the squared. So this here is huge, right? But now it's with a minus sign. So this means that this thing here is incredibly small, right? And so it's clear that this function here is continuous at 0. It's clearly continuous everywhere else. But actually it's, sort of using in this sort of argument, it's easy to see that this function f here is infinite differentiable. So you can differentiate it infinite many times, and even at 0. Okay. And of course the derivative is right. So it's an example of a function that looks like this: is dead 0 until 0, and then it goes up like this. Right. And so the derivative at 0 is 0. Any derivative, however many times you take the derivative of this function. Sorry, this thing here. If you take any derivative and you evaluate at 0, you always get 0. Right? So this means that if you're looking at the Taylor expansion, at 0, so you're looking at this k-1 Taylor polynomial. This polynomial is all of the coefficient in the polynomial is 0, right? So this polynomial is just 0. So this means that if you're looking at f of x, well, f of x is actually equal to this remainder term, right? So it's somehow, you know, the Taylor polynomial is like too trivial. It doesn't really help you all that much, right? So it's equal to this remainder term. Okay. Yep.
Is there a way of, so like the remainder, like bounding this helps us figure out how well the expansion approximates the actual function. Is there a way to determine like how far from the point you're approximating, like a or 0 in this case, you can go to a certain threshold?
Yeah, right, that's right. I mean, so you're asking, right, so you're asking, suppose, and you definitely could do this, right? You're asking, you're thinking that you're thinking a slightly different situation than here, but closely related, that you have some a here, and you have a function f, and you want to, and you are willing to maybe you're willing to take some fixed large k, and then you're asking, what I'm interested in, how well does this function, this polynomial, approximate this, but I want it within an certain area, right? So there's a given epsilon, and you're interested in how far away can you go from a so that this here is less than epsilon. And so this is, so this becomes a question of this remainder term, right? So this becomes a question of this remainder term. When can you always say that this remainder term is less than epsilon? And so like in this particular case, you would have to do it on a case-by-case basis. But in this particular case, the remainder term is, right, if this interval here, in that example over there, if you have here 0, this was a in our example, and then you want to go out here to some x, and now you know that c here is between 0 and x, but you don't really know anything else, right? So then it's like this remainder term. You will have this remainder term in this example at the c here. This again was equal to this thing here over k factorial. And so you would have that, you would want this thing here, rk c, you would want this to be less than epsilon. And so you would have that this thing here, the only thing you can really do is that you can say that c is less or equal to x. Yeah, that's right. That no. So you would do. So what you would do here is you would say r k c. This here has to be bounded by because c is less than x. So this is e to the x. You have to eliminate c. So you would do like this, k factorial times x to the power k. You have to eliminate c, right? Because you don't know anything really about c. And so this here now has to be less than epsilon. So now you only have, you have fixed your k, and so now you only have one variable, and you can solve that. Right? But you really have to eliminate c. Yeah. Okay. So again, how well the Taylor expansion approximate depends on the function. Okay, the next topic is another important topic, and so this is integrals. And there are different ways of defining integrals. This here is certainly one of maybe the most natural one. And so this is what's called Riemann. So it's after German mathematician Riemann integrals. And so the thing is that here now you look at a function. You have a function on some interval from a to b into r. And this function f here is bounded. And the idea is for integrals is that so you have a function and you want to be able to define area below graph. So if this is a function, you want to be able to calculate what is this area, okay? Now, if the function was to have crossed the x-axis, then this area here would count negatively, and this area here would count positively. Anyway, so this is what you want to do, and you're always starting with a bounded function. Now, to do that, right, and so you want to define that. The only thing that you know for sure is, so there's only like one ingredient you have. So only thing known, you know, at the outset. So the only thing you know is that if you take a right angle, so if this length here is let's call it D, and this here is E, right? Then you know that the area here, so area is D times E, right? Okay, that's the only thing we have. So now, how do we define the area below the graph? And to do that, we first need to talk about partitions. So partition. So suppose I have an interval here. A and B are real numbers, so I have an interval here. Then I talk about a partition. And it's useful to have a notation for a partition, so I call it P of this interval here. This is finitely many dividing points. And the dividing points always have to start at A and end at B. So you have finitely many, let's say K many, and you're looking at, okay, I'll write it K plus 1 many. So the first one has to be A. And then you have x1 up to the last one, and that has to be B. Okay. And so, so what you are thinking about is, so you have this interval here from A to B, and you have these dividing points, and you are thinking about dividing the original interval into these subintervals, right? So these are the subintervals, right? So you divide the original interval into subintervals. And the subintervals are, I'll do it like this. I will do it where I take from, it's always from, 1 to the next. And I'll write it typically where I'm starting, where I'm ending at I and beginning at I minus 1. So, right, so I'm dividing it into these subintervals. Right? So in this case here, where this is x0, there's going to be k subintervals, okay? And it's, you only always go from one to the next, right? So that's a partition. And now we need a second notion related to this, and this is a sub-partition. So sub-partition. Sub-partition, this is also sometimes called refinement. So a sub-partition is, so if you have a partition, so P1 is a partition, and then P2 is a sub-partition or refinement. If P2 has all the dividing points, of P1, and then some. I mean, right. I mean, of course, it could be a trivial subpartition where P1 and P2 are the same. That's okay. But in general, it would have some more points also, some more dividing points, okay? Now, right, so now let me look at, so what is then, so now let's try to get closer to try to define this with the area below the graph. Okay. So again, we have a function f from A to B into R. We assume that this is so that is bounded. We have P here is a partition of this interval here. Then we defined an upper and a lower sum. Then we define upper and lower sums. As follows. right? So again, you have a given function that is bounded, and you have a partition. And so we define upper and lower sums, and the upper and lower sums I will denote like this. It depends on the function, of course, and then on the partition. That's the upper sum. And the lower sum, similarly, I will denote like this. And so how are these defined? So they are defined as follows. That you have, here you have your interval from A to B. Then you have, this here is x0. Here I have x1. And here I have maybe x2. And then this thing here is then x3. So I take, I look at one of these intervals. Well, it could be this one here. It's between, in this case, it would be between x1 and x2. And I would look at the function in this interval here. And I would, so the contribution from this here would be that I would take, so for the upper sum with respect to this partition, the one that comes from this subinterval here would be the sup of f on this subinterval here. So the sup of the function times the length of the interval. Like that. So this would be the value that in the upper, that would come, in a minute I'll write it out more clearly. But this would be what is coming from here. And likewise, for the lower one, the contribution from this little interval here would be the inf of f. And then times. And the idea, right, is, okay, so that would be the contribution. The idea, of course, is that you have the only thing we knew was this with the area of a right angle, right? And so you have this function here, and you have some little interval here between xi and xi minus, xi minus 1 and xi. Right? And you're focusing on this little interval here. And you're looking at the function. The function was bounded. So there is a sup on this. And you try to look at the smallest right angle that kind of have the graph that fits, where the graph fits inside that, right? And then you're looking at, so this is the contribution from this little interval to P, to the upper sum. And then you have, right, that you're looking at the largest right angle like this that fits under the graph. And that's then contribution to the lower one, right? And the idea is that if the function is reasonable, if you're looking at finer and finer partition, then you should certainly get a better approximation to the area below the graph, right? I mean, and if the function is reasonable, these two, okay, so now what is then the, let me just define this. So this thing here, it would be convenient to the length of this interval to denote it by this. So this is xi minus 1. It's just the length of that interval. Okay, and so now written out, this thing, and okay, let me make one other notation. Mi is the sup of f on xi minus 1 xi. That's capital Mi. And little mi is then the inf on the same interval. like that. And so the upper sum for this partition, this is the sum from I equal to 1 to k of mi times delta xi. That's the upper sum. And the lower sum is then the sum from I equal to 1 to k of mi delta xi. Okay, so that's the upper and the lower sum. Okay, the first thing you observe is a trivial fact, and it's that really should be the case, because one is like what fits inside the graph, below the graph. The other is where the graph fits below the right angle. So you clearly have and this is just because this number here is the inf, this is the sup on the same interval. So you clearly have that LFP is less or equal to UFP, right? So this is clear, right? Okay. Let's look at a couple of examples. So just to make sure that this is totally clear, let me look at a couple of examples. So the first example is, so I take a function f of x equal to x squared plus 1. And my partition and the interval here, I'm going to think about this as a function on -2 to 2 into R. And my partition here is going to be -2, -1, 0, 1, and 2. Right, and so you have, so let's see, so this here, so if I draw the function, then this looks like, if this here is 1, here you have 1, then it looks sort of like this. Doesn't more or less like this. Okay, and so this means that here you have 2, and this here is -1, and here you have -2. So now, if you're looking at right, so this means here that, so this is my partition. So this means that x0 is equal to -2, x1, that's the next one, is -1, x3 is the next one, that's 0, x4 is 1, and x5 is 2, right? And so, of course, all of these intervals here, right, they all have the same length in this case. So xi minus 1, this was what we call delta xi. This here is, for each of these, is equal to 1. And now we have that when you're looking between -2 and 2, -2 and -1, so on this interval here, the function on this interval here is decreasing, so the largest value is achieved at this point here, right? M1, this is the same as the sup of f between x0 and x1, and so this is the same as the sup of -2 to -1, right, of f, and the function was decreasing, so on this interval, so the largest value is achieved here, and that's 5. Right, so this here would be 5. And on the second interval here, right, so this is between -1 and 0, still decreasing, so the value is, the largest value is here, where it's 2. So this here is 2. And M3, this is now between 0 and 1, so now it's increasing, so the largest value is over here, so that's again 2. And then the last one is again 5. Right? And then likewise for the ones that are the infimum. So the first one, M1, well, the function was decreasing, so the smallest value is over at this endpoint. There the value is 2. So you're getting, this here is 2. And then between -1 and 0, it's still decreasing. So there the smallest is at this point where it's 1. So this is M2. And then M3, this is now, here the function is increasing, so it's still the value here. So it's still 1. And then the last one is between 1 and 2. And there it's the infimum is the value here, so that's 2. Right. And so you see that in this case, the upper for this function, for this partition, it's this, right, all of the intervals have lengths, these small intervals have length 1, so it's just the sum of these guys, right? So this is just equal to 5. It's, if you will, it's 5 times 1, that was the length of the interval, plus 2 times 1, plus 2 times 1, plus 5 times 1. So in other words, you get here 14. And for the lower ones, it's, again, this time I want rise times 1. It's the sum of those guys, and that's actually 6. Right? So that's upper and lower sum. Okay. Now, and we had one observation that was an immediate observation, and that was this thing here. Now, what is useful is that you're starting with a partition, and then you have a sub-partition. So the next one is, so I take a function f on some interval from a to b, and this function here is bounded. And then I have p is a partition. P1, say, is a partition. And then P2 is a sub-partition of P1. And now the thing that is useful is the following. That, so the following claim, the following lemma here. That if you take a sub-partition, then I claim that the value of the upper sum go down and the value of the lower go up. So this is the following. So lower of f times p1 this is less or equal to the lower of f of p2, we already proved that this thing here, this one here, this inequality we haven't proved yet, but this one here we have, that this is less than the upper one for the same partition. And the second claim is that this here is then less than the upper one for the first. Okay. Now, why is this the case? This is also actually a trivial statement, but it's a very useful statement. So imagine that you have your partition P1 here, and then you have the dividing points I minus 1, and here you have I. Right? P2 is a sub-partition. So there may be intervals like this where there are no further dividing points. Right? But in that case, the contribution that for the lower and upper is the same for the two partitions. Right? But should there be one or more, let's just say there's one, right? Then for the upper one, you would look at, you would then get, so you would get a new dividing point. Let's call it y. And then you would get, for the new one, you would look at the sup here on this interval here, right? But the sup on this interval here of the function is less than the sup on the larger interval. So you would get a sup of f on the interval from I minus 1 to y of f. You get that, and then you would get times the length of the interval, that's y minus xi minus 1. And then you would get a second sup, but this is now from y to xi of f, and then you would have multiple by the length of this interval. So this here is then from xi to y. Okay? So this is what you get from the new partition, the contribution from the second, this is the contribution that you get from the upper sum for this partition P2 from this part, right? But now you see that this thing here, the sup over this little interval, well, that of course is less than the sup over the larger interval. So this is less than mi, and I just keep this one here. And this one here is also a sub-interval of this larger interval. So this is less than mi again, times xi minus y. But now you can factor out the mi. So you're getting mi, and you're getting the sum of these two, y minus xi minus 1 plus xi minus y. And so you see that this here is exactly mi times xi minus minus 1, right? And so you see that the contribution that we get here to the upper sum from this part here, that was this and this, those two things. This is less than the contribution we get from the upper sum from the first partition, right? And so this proves this inequality here. And this inequality is just similar, right? It's just with the int instead of the sups. Okay, so this is like a key point. It's each of these steps is like completely trivial, but together it actually means that you can really define something non-trivial. Okay, so now, and this may seem cheating. Now well, first of all, we define the upper and lower intervals. So we have upper and lower sum, and now we define the upper and lower intervals. So upper and lower integrals. Okay. So the upper lower integral, so the upper here is denoted like this. We take a bar over this, and this is the upper lower integral. So this is the integral, this is the function, and then you write this. And so this is simply defined to be the infimum over all partitions of the upper integral. Upper sum, sorry. Right, and so remember again that if you take a partition and you refine it, if you're looking at a sub-partition of the given partition, then this number here goes down. Right? I mean, it may stay the same, but it's certainly not bigger. Right, so this is, so the idea here is that essentially this number here you get by looking at finer and finer partition, right? So idea is that the infimum that this is a limit over finer and finer partition. Right, so that's the idea. It's sort of but the precise statement is that it's just the infimum. Right? So this is the upper integral, and then likewise we define the lower integrals.
Is there any assumptions that like you have finitely many partitions, or like obviously?
Right. It's not, you know. But there is a key assumption is that for each partitions there are only finitely many divisions. But there's not but there are infinitely many partitions. So it's really and so when I say that it's a limit over finer and finer partitions, you should really think about that in sort of quotation mark. This is not a very precise statement. Okay. So but the precise statement is just that it's infimum over all partitions. Yeah. And so, I mean, you can make that precise, but then that requires a lot of stuff that we don't want to do here. And there's no reason to it, because there's a perfectly reasonable way of defining it. And so that was the upper integral. So this is the upper integral. And then similarly, the lower integral. The lower integral, and there I'm just putting the bar below. And you define it like this. And this is now the sup, right? Because remember that if you took a partition and then you take a sub-partition, then this lower sum actually went up. So it's a sup over all partitions of these lower. Okay. Right, and so now we say that, and then we say that, so now here's the definition, and again, this may initially seem like kind of we are wimping out, but in a minute we will then determine when this is the case. So we define, so f here, so if you have a bounded function like this, then we say that f is Riemann integral. So if the lower sum is equal to the upper sum. So if this here is the case, and in that case, and then the Riemann integral is this common. So the Riemann integral is written like this, and this is just this common value. All right. Okay. Now, one thing I just want to remark is that you always have that so one remark is that so note that so first of all we had this trivial statement that if you take a partition, then the lower sum is less or equal to the upper sum, right? Then we had that if you took a sub-partition, if this here was a sub-partition, of P1, then this lower sum here, under a sub-partition, the lower sum went up, but it's still staying below. So you have this inequality here. Okay, now what is this useful for? So as a consequence of this, we get that whether or not the function is Riemann integral, you always have that the lower integral here of f dx is less or equal to the upper integral. So this here is for all functions. And why is this the case? This is because if you take this here is the sup of these lower partitions, right? But if you take any given partition, then this lower thing here is less than the upper one. Right? And so now imagine that you take, so if you take a lower partition, right, suppose now that you take the sup over all partitions. Then it means that there is one partition so that this value here is close to the sup. But for this one here, right, you have this inequality here, right? And so in fact, if you take any other partition, you can think about it. Maybe I'll explain this more detailed next time because I only have a minute. But it basically comes from this inequality here is coming from this inequality here. It will take just a few minutes to explain it clearly. So maybe I'll just leave it here. But a key point here is that you have this inequality here. And it comes from that. Right? But we'll return to that next time because it's to make it really clear, it will take a few minutes. Now, the last thing I want to say is that so you may think that we sort of wimped out of saying when this right, because we just define it. We just say that it's Riemann integrable if those two things are equal, right? And so, but then the question, of course, becomes when are those two things equal, right? So that's the key question. So the key question is when are they equal? And we'll answer this next time, where we will show that if f is continuous, then they're equal. Okay. And so anyway, so I'll return to this. I will first, we need anyway some more information about this upper and lower integral, and I will first show why the lower one is less or equal to the lower one is less or equal to the upper one always, right? And then we will talk about, some criteria for when they are equal, and then we will prove this for continuous functions.
Is that if and only if, or are there other cases?
No, it's not. It's not. It's not. It's not a total answer. It's a good initial answer. But there are many functions that are not continuous, that are very worth, that plays key roles, and they're still. And we will also look at an example. It's in the notes, but I didn't get to it. We look at an example of a function that is not where you don't have this equality, and this is like an old